Hello guys, welcome to the 14th class of this course. In the last few classes, we talked about the Hamilton's principle. So there we defined the action. So action is defined like, so if I is the action, it is defined like integration I dt from point 1 to point 2. Sorry, it's L dt. L is the Lagrangian. So this I is the action. And if we want to extremize, so if we choose, so point 1 and point 2 in the space of generalized coordinate, this point 1 and point 2, it represents 2 points at some different time. Let's say at time t1 and at time t2. So in generalized coordinate, if a particle at time t1 is at point 1 and at time t2 at it is at point 2, then the path followed by the particle, so there can be a lot of paths we can draw, right? So infinite number of paths we can draw. But let's say this is the actual path that the particle should follow. So let's say this is the actual path. So in that case, if we choose the actual path, then Hamilton's principle says that delta I has a stationary value. The action has a stationary value. That means delta I equals to 0. So from there we derived an equation like, so if the Lagrangian only depends on it's only a function of, so y t alpha y dot t alpha t. So alpha is the path variable. So it's kind of it. If we change the alpha, the path will change. Okay. So in that case, so from there we derived the equation like, so if delta I is equal to 0, this is the Hamilton's principle. And if Hamilton's principle is satisfied, then this L, okay, there is a dt. So if the Hamilton's principle is satisfied, then this L Lagrangian should follow an equation which is ddt of del L del y dot minus del L del y equals to 0. So using this idea, in the last class we did two problems. One is finding the smallest distance between 2 points, and another is the minimum surface of revolution. Today we will do a very interesting problem, which is called the Brachistochrone problem. So Brachistochrone problem. First of all, let's define the problem. Okay. The problem statement is, if a particle is falling from rest under the influence of gravity, and it travels from a higher point from a higher point to a lower point, the path need not be vertically downward. Then what will be the curve joining the 2 points for which the time of travel is minimum. So this is the statement of the problem. So let's draw and understand it. So let's say this is our axis. This is our x-axis. And let's draw the y-axis in the directing downward. So because the particle is moving from from a higher point to a lower point. So let's say here the particle was initially here at point 1. This is the point 1, and after some time the particle is falling. So particle is at point 2, and there can be lot of paths. So let's say there can be lot of paths. This can be a path. Uh, this can be a path it can follow. This can be a path it can follow. So there can be a lot of paths the particle can follow. What we want to calculate is like along which path the time taken to travel from this point 1 to point 2, that will be minimum. Okay, so let's say it follows this path. So in that case, let's say this is a point. So at this point, so let's say at some time the particle is at this point. So here the velocity of the particle is given by v, and this this length, so this infinitesimal distance, this is given by ds. Okay, so then what is ds? Ds is root under dx square plus dy square at this point. So at this point. Okay, and at this point the velocity is v, which is given by dy. The velocity is given by let's say the velocity is given by v. Okay, the velocity is given by v. So in that case, the time required to travel this infinitesimal path. So here ds is the infinitesimal path. ds is the infinitesimal, means very small, tends to 0. Then the time required to travel this infinitesimal path will be dt equals to ds by v. Okay, ds is the distance traveled and v is the velocity. So we'll assume that the path is so small the velocity is not changing during this path. So now what is V? We need to calculate the V. So the particle is falling under gravity. In that case, and initially it was at rest. So if the particle fall at a height y, okay, so if the coordinate of this point is xy, so in that case, the particle has fall a distance y, a vertical distance y. So in that case, the change in potential energy or the loss in potential energy will be mgy, and this loss in potential energy, that will be the gain in the kinetic energy, because the gravitational force is a conservative force. So in that case, the total mechanical energy will be constant. So the potential energy lost, that will be the gain in kinetic energy. So the kinetic gain in kinetic energy is, so here the kinetic energy is kinetic energy was zero because there was no velocity, particle was at rest at this point, at point 1. So here the kinetic energy is half mv square. So the gain in kinetic energy will be half mv square. From this relation we can write, so m will be cancelled. So here we'll cancel the m from each side. In that case, v will be root under 2gy. So in that case, dt will be ds by root under 2gy. So the total time taken t from point 1 to 2 will be integration dt from point 1 to point 2 equals to integration point 1 to point 2 ds, which is dx square plus dy square root under dx square plus dy square by root under 2gy. Now it will be integration from point 1 to point 2. So we can take this dx square out, so it will be dx because there is a root. So in that case, we will get so this dx we are taking out. So in that case, 1 plus dy dx whole square times dx by root under 2gy. Now we will write this dy dx. So this dy dx we will write it as y dot. So dy dx is not y dot is not dy dt. It is dy dx. Okay. So y dot is dy dx. So we want to minimize this. Minimize it. That means we can treat it as our action. So in that case, we can treat this quantity as our Lagrangian. Then, if this action have a minimum value, have a extremum value, Hamilton's principle says, from the Hamilton's principle, we show that this Lagrangian, it must follow the following equation. So let's call it f. So f must follow the following equation, which is ddt of del f del y dot. It's not ddt, it's ddx. Because x is the independent variable here. Minus del f del y equals to 0. And f is root under 1 plus y dot square by root under 2gy. Now if we do the derivative, then we will get ddx of del f del y dot. So if we derivative it with respect to y dot, there will be root under 2gy. This 2gy, there is no dependence in y dot. The y dot dependence is here. So if we derivative it, we will get half root under 1 plus y dot square 2 y dot minus. If we derivative it with respect to y, so this term it will be root under 1 plus y dot square by root under 2g times minus half times 1 by y to the power 3 by 2 equals to 0. So here we will get ddx of y dot by root under 2gy times root under 1 plus y dot square minus, so minus minus plus half into root under 1 plus y dot square by root under 2g y to the power 3 by 2 equals to 0. Now this root under 2g, it's a constant. It has no dependence on x. In that case, we can take it outside, and if we multiply by root under 2g both side, so in the right hand side it will be 0. Then we will get ddx of y dot root under y times root under 1 plus y dot square plus root under 1 plus y dot square by 2y to the power 3 by 2 equals to 0. Let's call it equation 1. Now we will propose that the solution of this equation 1, so it's a little difficult to find out the solution from directly from here, solution of the path, but we will propose that the solution will be like this. So x will be a phi minus sine phi, where phi is the variable here, and y is equal to, it's a parametric solution, 1 minus cos phi. Okay, a is a constant. So now what we will do is, we will show that this equation, this value of this expression of x and this expression of y, it will satisfy this equation 1. Okay, so then we can say that, okay, this is a solution of this equation 1. So this is the desired path where the time taken will be minimum. So let's calculate dx d phi. It will be a1 minus cos phi, and dy d phi will be a sin phi, right? In that case, dy dx, it will be sin phi by 1 minus cos phi. So now we will calculate this term first, okay? And then we will calculate this term, and we will show that, so the value of this term is exactly the negative of this term. As a result, it will follow equation 1. So first let's calculate y dot by root under y times root under 1 plus y dot square. Y dot by root under y times root under 1 plus y dot square. So it will be sin phi by 1 minus cos phi by root a root under 1 minus cos phi times root under 1 plus sine square phi 1 minus cos phi square. Now this will be sine phi. Now from this term, there will be 1 minus cos. If we add them, if we add it with 1, so this term, if we add it with 1, then this 1 minus cos phi square, and there is a root. So there will be a 1 minus cos phi here. So it will go above, and this 1 minus cos phi will get cancelled with that term. In that case, in the numerator, we will get only sine phi. This term, so this terms will be there. Root a root under 1 minus cos phi times root under. So if we add it with this one, then this term will be 1 plus cos square phi minus 2 cos phi. It's the formula of a plus b, a minus b whole square, plus sine square phi. And there will be a, so this term, so there will be also this this term square 1 minus cos phi square will be there, and which will get cancelled by this term. Okay, so now sine square theta, sine square phi plus cos square phi, it will be 1. There is already a 1 here, so then 1 plus 1 will be 1 plus 1 will be 2. So and then 2 minus 2 cos phi. So we will take 2 common, then we will get sine phi by root under 2a root under 1 minus cos phi. So if we take 2 common, there will be another 1 minus cos phi, right? So 2 minus 2 cos phi. So if we take 2 common, then we will get 1 minus cos phi. So there is a root 1 minus cos phi. There is another root 1 minus another root 1 minus cos phi. So in that case, we can write it as 1 minus cos phi. Now, if we take the ddx of this term, so we take the ddx of this y dot by root under y times 1 plus y dot square, it will be dx d phi dx by dd phi of y dot root under y 1 plus y dot square. So we are changing the variable here because this term, so we are changing the variable here. We are taking the derivative with respect to phi. This is because this term, this y dot by root under y times root under 1 plus y dot square, we know this term as a function of phi. So we can derivative only if, I mean, when it will be easier to derivative if we take the derivative with respect to phi. Okay, and this d phi dx, which is 1 by dx d phi. So we know the value of this dx d phi here. So this dx d phi, the value of it is known already. So and this y dot by, so this term, it will be this term. We already showed that this term equals to this term. So we just rub it and put this term. Now dx d phi will be a times 1 minus cos phi, right here, dx d phi, and this d phi dx, it is 1 by dx d phi. So that means this d phi dx will be 1 by a times 1 minus cos phi. Now we need to take the derivative. So this root 2a, it's a constant, so we can put it outside. Let's put it outside. And then the derivative, which will be 1 minus cos phi whole square. This term intact, derivative of this term, which is cos phi, 1 minus cos phi, minus this term intact. So this term intact, derivative of this term, which will be sin phi times derivative of this term. It will be, so derivative of 1 is 0, and derivative of cos phi with respect to phi, it will be minus sin phi. There is already a minus, so it will be minus minus plus. It will be sin phi, which will be sin square phi. And this minus is coming because of the formula. So derivative of dd phi, derivative of some function by some function, so then there will be a minus sign. So now look at this term. What we will get? There will be a cos phi if we multiply cos phi with 1, and there will be a minus cos square phi if we multiply this cos phi with this cos phi. And there is also a minus sin square phi. So in that case, if we take the minus common, it will be cos square phi plus sin square phi, which is 1. So a1 minus cos phi put under 2a. Here, what we will get is cos phi minus 1. 1 means sin square phi plus cos square phi. And here we are getting 1 minus cos phi square. So in that case, it will be minus 1 by root 2 a to the power 3 by 2 times 1 by 1 minus cos phi square. So that's the value of this ddx of y dot by root y times root under 1 plus y dot square. Let's call it equation 2. And now we will find out the value of, the second term of equation 1. Okay. So second term is root under 1 plus y dot square by 2 y to the power 3 by 2. Second term is root under 1 plus y dot square by 2 y to the power 2 or a 2. Now it will be root under 1 plus sin phi by 1 minus cos phi square. So this value we already calculated, y dot, value of y dot. That means dy dx. So this is y dot dy dx. It is sin phi by root under 1 minus cos phi. That's what we wrote here. And this y to the power 3 by 2. So let's see the value of y. Y is a times 1 minus cos phi. So there will be a to the power 3 by 2 times 1 minus cos phi, which will be 1 by 2 a to the power 3 by 2, and here, so there will be 1 by 1 minus cos phi, and here it will be 1 minus cos phi, and so this 1 minus cos phi, here it will be 1 minus cos phi square, but there is root also. If we add them, if we add 1 with this term, then there will be a 1 minus cos phi square in the denominator, and there is root, so there will be 1 minus cos phi. And in the numerator, we will get again this 1 minus plus cos square phi minus 2 cos phi plus sine square phi root under. Now this cos square phi plus sine square phi, which is 1, and there is already a 1, so it will be 2 minus 2 cos phi. And if we take this 2 outside, then there will be a root 2 times root under 1 minus cos phi. This root 2 and this root 2. So this root 2 and this root 2. So because these two. So as a result, uh, there will be only one root 2 in the denominator. And here, this is, so I made a mistake here. So this y to the power 3 by 2, in that case, this a to the power 3 by 2 times 1 minus cos phi to the power 3 by 2. There is 3 by 2 here. Because here y to the power 3 by 2, I wrote a to the power 3 by 2. So y means a times 1 minus cos phi. So both have a power of 3 by 2. So we can write we can write this term as one minus cos phi to the power half. So as a result, we will get 1 by root under 2 a to the power 3 by 2 times 1 minus cos phi square. So this is equation 3. Let's call it equation 3. So now you can see, like, equation 2 and equation 3, if you look at it, then you will see that this term, the value of this term, is exactly the negative of the value of this term. Let's see, these are the same value, only there is a negative term. Okay. So in that case, if we add these two terms, this term and this term, we will get 0. That means if so if we add equation 2 and equation 3, then we can easily see that our proposed solution satisfies equation 1. Okay. So then the solution is basically x equal to a phi minus sine phi, and y2 is equal to a 1 minus cos phi. So these two equations, these are called the equation of centroid. So if we draw it, x versus y, the path will be, this is x, this is y. Let's say this is the starting point and this is the ending point. This is the, let's say, ending point. This is the point 1 and this is the point 2. In that case, the path followed will look like this. Yeah, sorry. Will look like this. So if we extend it, the equation will be like this. Equation will be like this. Okay. But up to this point, from point 1 to point 2, it will follow this path. So up to this point 1 to point 2 will follow this only this path. Now, if we plot it further, you will get this curve also. This. So here its value is 2a. At this point, its value is pi a. Its value is 2 pi a. So this is the desired curve that it should follow, such that the time taken will be minimum. Okay. So this problem is called the Brachistochrone problem. It's a very interesting problem. So our next job, we will derive the Lagrange's equation from this Hamilton's principle for several number of generalized coordinates. So we have it's a generalized derivation of this Lagrange's equation. So again, there will be action. Equation 1 to 2. So from point 1 to 2, and this if will depend on different y1, y2 dot 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 y1 dot y2 dot 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 t dt. So there are multiple generalized coordinates here. Y1, y2, y3. It can be a n number of coordinates. And it can be anything. So now if y1 t0 is the actual path, so then this alpha, we can introduce the alpha such that which will vary the path. Actually, it will be the actual path plus some alpha times eta 1 t. So eta 1 it can this eta 1 it can be any function. This alpha is changed to 0. Alpha is a very small deviation from the actual path. Okay. Similarly, for y2 t alpha, we will get y2 t0 plus alpha eta 2t. So if we have n number of such coordinates, it will be that much number of equations. So now for all I, eta I at t equal to t1 will be eta I at t equal to t2 will be 0, because at the starting point and at the ending point, all the paths that will meet. So if we take this, so these are the initial point and this is the end point. So if we take this path, whether you take this path, whether you take some other path, whether you take another path, so the starting point and end point, so at point 1 and at time t1 and at time t2, all the values will be same. Okay, the destination and the starting point, these are the same. So then this is the condition, this will be the condition on etas. So now we will use the so if we calculate the del j del alpha from 1 to 2, then there will be a summation over I del f del yi del alpha plus del f del yi dot del yi dot del alpha times dt. Okay, summation over I means, so the number of y is present. So there, if there are n number of this coordinates, in that case we will be n number of this I will go from 1 to n. For each y, so y1, y2, y3, we will get this kind of terms, which will be sum. So now if we look at this second term, so if we look at the second term, it will be integration from 1 to 2, this del f del y dot I del yi dot del alpha dt. Now if we so this yi dot, which will be dy dt. So here t is the independent variable. So y dot means dy dt. So here we get 1 to 2, and t is independent of alpha. So you can write it like del 2 yi del alpha del t, and they can commute. So in that case, it will be, you can write it as del t del alpha. Now if we do the integration by parts, we will get first term intact, integration of the second term, limit, put the limit letter, integration of the second term, del 2 yi del t del alpha dt from point 1 to point 2 minus integration from point 1 to point 2 ddt of del f del yi dot times, this integration will be del yi del alpha del yi del alpha dt. So now look at this term. This integration will be del yi del alpha, right? So we can write it directly here also. Del y by del yi by del alpha. Now what is del yi by del alpha? Here look at this equation. Del y1 by del alpha, it will be eta 1, because this doesn't depend on alpha. So for any yi, del yi by del alpha will be eta I. So then this term, it will be eta I t. Now if we put the limit is from point 1 to point 2, then we will get eta I t1. There will be a term which include this eta I t1, and there will be another term where we put the lower limit. So that will be dependent on eta I of t2. So both of the term will be 0, because eta has this condition. Eta needs to satisfy this boundary condition. So then this whole term, after we put the limit, will be 0. Then we will get minus of 0.1 to 0.2 ddt of del f del yi dot del yi del alpha dt. There is a minus sign here. Now put this value. So put the value of this into this del j del alpha. Then what we will find? We will find this del j del alpha. It will be del j del alpha. It will be integration from point 1 to 2 sum over I. Then this del f del yi del f del yi minus ddt of del f del yi dot, and we can take this del y del alpha common, because this term there is del yi del alpha, and here also there is del yi del alpha. So we will get del yi del alpha dt, right? So now delta j, the variation of this action, which will be del j del alpha d alpha, it will be integration from point 1 to 2 sum over I del f del yi minus ddt of del f del yi dot del yi del alpha d alpha. So now, according to Hamilton's principle, let's write it clearly. Hamilton's principle, if we are at the actual path, then delta j equals to 1 to 2 I del f del yi minus ddt of del f del yi dot. What is this del yi del alpha? Let's look at this equation again. Del yi del alpha, it will be eta I. This term will be eta I t d alpha dt. It will be 0 if we are at the actual path. Then the variation of this action will be 0, because action will be stationary. So then this eta I, this eta can be any function. So for any function, if we vary this eta can vary, so eta can be anything. So if eta can be anything, in that case, if the integral is 0, then this term, it must be 0. So if eta I t is any function and all eta i's are independent, and all eta i's are independent, then if the integral is 0, in that case, it will satisfy, it must satisfy if must satisfy this equation. Okay, this is the Lagrange's equation derived from the Hamilton's principle. Okay, so here so what is this eta I d alpha? It is basically, so this eta I d alpha, it is basically the virtual displacement delta y. It's not the actual displacement, it is a change of configuration. That's how we define the virtual displacement, right? So here it is a change of path. We choose another, if we vary the path infinitesimally, that's the variation delta y, virtual displacement. So now if, so f is termed as L and this yi, it is termed as a generalized coordinates qy. So then we will get this del L del qy minus ddt of del L del qy dot equals to 0, or we can write ddt of del L del qy dot minus del L del qy equals to 0. This is the Lagrange's equation of motion. From Hamilton's principle, we derive this. Okay. So today we solved the Brachistochrone problem, and then we derived the generalized Lagrange's equation from the Hamilton's principle. In the next class, we will solve some very interesting problems with this Lagrange's equation of motion. Okay. So that's all for today. Thank you.